Hello and welcome back. You might have noticed that when the sign of the first derivative changed, we sometimes had these peaks, or sometimes had valleys. So we had like a high point on the graph or a low point. These are called local extrema. They're extreme values, at least in a local sense, kind of like the top of a hill or the bottom of a little valley. Now they may not be the absolute maximum values of the functions, like they're not the Mount Everest of the y values necessarily, but they're just local peaks and local valleys. So a peak is called a local maximum and a valley is called a local minimum. Now looking over at the graph of function f on the right, we can start to identify the local maxes and local mins, the local maximum values and the local minimum values. So for example, as we're reading the graph from left to right, we notice that there's a little peak right here at x equals 1. So that would be a place where we have a local max. Now as we're again moving from left to right, we see that at x equals 3, there's a local min. Where's the next max or min as we're moving to the left, or as we're moving to the right? If you said 4, that's correct. At 4, you have a local max. And the next one? If you said 6, you have a min, then that's correct. So this graph has 2 local maxes and 2 local mins. Now again, these are not necessarily the biggest function values or the smallest function values of the entire graph, but if you just look locally around x equals 1, that's going to have a peak right there, right around x equals 1. So locally, close by. Sometimes they're called relative maxes and relative mins because they're relative to the x values around them. Now the one thing to notice is that to have a max, the graph has to be going up, it has to be increasing on the left side, and then decreasing on the right side. So it has to be going from increasing to decreasing as you cross that max. It's really the only way you can get a max is to go up and then down. And to get a min, the only way you can get that happening is if you're going down and then up. So in other words, if you're decreasing and then increasing. Remember, we're always moving to the right when we're talking about increasing and decreasing. So you can see for this max, the second max, we're increasing and then decreasing. And then for the second min, we're decreasing and then increasing. So maxes happen when you go up and then down, mins happen when you go down and then up. Now the formal definitions, the more formal definitions for local maxes and local mins of a function f with a domain D, so D is the set of all possible x values that can be plugged into the function, are like this. F has a local maximum at C inside of D. So this just means that this is an x value inside of our domain. This symbol means an element of or is in. So at C in D, if the function value at C is bigger than or equal to all the other nearby function values. So f of C is greater than or equal to f of x for all x in D in some open interval containing C. So just locally around, the open interval containing C is just locally around x equals C. It doesn't have to be the whole domain, just has to be the x values that are close by C. So basically it's just saying if it's the biggest function around, if it's the biggest function in the neighborhood, then that's a local max. And then f has a local min at a C value inside of our domain if f of C is the smallest function value around. So if it's less than or equal to all the other function values that are nearby. Now, as we mentioned, to have a local max, the function needs to be increasing and then decreasing, and to have a local min, the function needs to be decreasing and then increasing. So where might a function have a local max or a local min? Well, the places where the first derivative might change signs, and that would be f prime equals 0 and f prime does not exist. the same places where we looked to determine whether a function was increasing or decreasing, or at least to find those intervals where the function was increasing and which ones were decreasing. So to find local maxes and local mins, our problems are going to look very similar to example 1. Before we get to the next example, though, this kind of idea is summarized in the first derivative test. So it says, suppose f of c is defined, so c again is just some x value, and f prime of c is either equal to 0 or it does not exist. So those would be like, this is an x value now where the graph might be changing from increasing to decreasing or decreasing to increasing, in which case we might have a max or might have a min. Well, one of these 4 situations would have to happen then. So the first possibility is that the graph could be increasing and then decreasing as you go through that point that's at x equals c, in which case you would have a local max right there, as we discussed. Another possibility is that the graph could be decreasing and then increasing, in which case you'd have a local min at that point. But then there are 2 other possibilities. What if the graph is increasing, goes through this point, and then continues to increase? That can happen, for example, if you look at x cubed, which goes increasing and then has a horizontal tangent line at x equals 0, and then continues to increase. So there, you don't really have a max, you don't really have a min either. You would just say not a local extrema. Or the other way it could happen. The graph could be decreasing through that point and then continue to decrease after that point. So in that case, again, not a local extrema, not a local max or min. So it really boils down to just the sign of the first derivative. Notice that I've laid these out kind of like we worked out example 1 in our sign analysis. So we're going to write it out the same kind of way. So example 2 says, find the local max and min points of f of x equals 2x to the 4th minus 4x squared plus 3. Oh, good, got this. All right, first thing we're going to do is find the derivative, which is 8x cubed minus 8x. And the derivative of 3 is 0. So in a moment, we're going to be trying to figure out where this first derivative is equal to 0 and where it possibly does not exist. And so we're going to want to have this in factored form. So let's go ahead and factor this. There's an 8x in common. Then we can factor x squared minus 1 as x minus 1 times x plus 1. And now we can go and think, okay, where is the first derivative equal to 0? And where is the first derivative dne? Where does it not exist? We always want to be thinking about those 2 possibilities, because those, if either of those happen, those give you x values where we might have a max or a min. Setting the first derivative equal to 0 is pretty straightforward once we've got it all factored like we do. We just set each factor to 0, and we get x equals 0, x equals 1, and x equals -1. Now the first derivative dne, well, there's nothing really that can go wrong here with x values. Any x value you can plug it in, any real number you can plug in for x. There's no division by 0 or anything like that. So the first derivative does not exist. Well, nowhere, or you can just write none. There are no x values where the first derivative does not exist. Let's take the x values that we did find. Candidate x values where the sign of the derivative might change. I'm going to write them in order, -1, 0, and 1. Make a row for our first derivative. Just write f prime, which was 0 at each of those x values. So again, this row is capturing all of the values, all the outputs of f prime. And then we just have to figure out what the sign is. Give me a sign. What the sign of f prime is in each of these intervals. So we can take like -2, for example, and plug it into the first derivative and see what the sign is. Let me do that work down here on the bottom. F prime of -2. Well, there, if we plug in -2, we're going to get a negative times a negative times a negative, negative times negative times negative, which is negative. Will the sign change as we cross x equals -1? Yes, it will. Because the corresponding factor x plus 1 has an odd exponent. Will the sign change as you cross x equals 0? Yes. Because the corresponding factor x has an odd exponent. And will the sign change as you cross x equals 1? The answer is again, yes, because as you cross x equals 1, the corresponding factor x minus 1 has an odd exponent, so odd multiplicity. So we quickly got out this sign analysis for the first derivative. Now at this point we could write out the intervals of increase and decrease, but that's not what we're asked to do. We're asked to find the maxes and mins, the local maxes and local mins. Now just to help out, because we're not going to be given the graphs of these functions, those are just there for reference when we're taking notes. Just to get an idea of what the graph is going to look like, we can use the first derivative signs to tell us if the graph is increasing or decreasing. So when the first derivative is negative, what does that tell you? The graph is decreasing. And when the first derivative is positive, what does that tell you? The graph is increasing. So then on the next interval, negative first derivative, so decreasing, and then positive first derivative, increasing. This can help you visually just get a feel for what's going on here. We're going to, again, make this even finer tuned in the next section when we look at what the second derivative will tell us about the graphs of functions. But here, if we're just looking for maxes and mins, we can see that happening. Here, the graph is going down and then up, so we have a min happening at x equals -1. Let me write that down. Min at -1. Now it did ask for the points on the graph, so here the x coordinate is -1. To get the y coordinate, you would just plug in -1 into the function, and it turns out you'll get 1. So let me just mention where we got 1. We got this by plugging 1 back into the original, plugging in -1 back into the original function. So that would give you 2 times -1 to the 4th. Here, let me zoom up here. So 2 times -1 to the 4th minus 4 times -1 squared plus 3. So minus 4, I already forgot what I just said. Minus 4 times -1 to the squared plus 3. And you get 1. At x equals 0, do we have a max or a min? If you said max, that would be correct. 0, 3. Again, you plug in 0 into the function to get 3. And then what about at x equals 1? Max or min? If you said min, that would be correct. 1, it turns out the y value is 1. So there are our max and min values, or the points at which we have maxes and mins. Now the graph confirms all of this. We have, when x goes from -∞ to -1, the graph is falling down as you go to the right. It's decreasing. There's the negative sign that tells us it's decreasing. The slope of the tangent line is 0 at x equals -1. So that's the 0. And we can see that we have a, and then it starts to increase from -1 to 0. The graph increases, which is what we're seeing. And right there at the bottom is where we have our min. Our min is at -1, 1. So that all matches exactly what we found. Then the graph has a max at 0, 3. Then it decreases and then increases, making a min at 1, 1. So we found all the maxes and mins of this graph. All right, thank you for watching, and see you next time.